All right, you guys. It's 4:30. Last time I hit record, I just got back from hitting legs. And it was a disappointing day of 3D printing. Not a complete fail, but 3/4 of a failure, only 25% passing. That is to say, I had 4 files and 4 3D printers reserved. One was for the board enclosure box. One was for the board enclosure lid. One was for the Scotch yoke, is what I've been calling it. The crank, the lever, and 2 pins with 2 washers or nuts. And then one machine was reserved for my modified motor mount and a total of 6 more nuts, 6 more screws or bolts and washers, whatever you want to call them. Only the lid ended up working out, and I'm going to tell you guys why. So here's the lid, and it turned out decent. You might not be able to see, but it's kind of like, I wouldn't say warped quite yet, because we're going to get to the warped piece here in a sec. But there's kind of like this wrinkling, or it seems to me, I'm not like a 3D printing expert, like you can see kind of maybe here on the edge, it's not as good as like the other side on the very edge, right? You can't really tell if I'm just waving it around, but you can kind of see, right? Like it didn't turn out 100% quality wise. And it seems like a lot of this has to do with thermal problems. Like the material is getting laid down and it's hot, and then it's like shrinking because of like the ambient temperature and where the room where those 3D printers are. But this is the only piece that worked out. So this would be the top of the board enclosure, and I gave it like a lip, and I didn't get the board enclosure box to print, so I have no idea if like this lip tolerance will have it like sit on there properly. But I give it like little thumb holes, so that you can put it on, remove it relatively easily in theory. Okay, but the plus side of this is that, okay, I'm not putting the lapel mic on, because sometimes with like these shirts it'll just like hang off. But okay, so I have here part of my setup, which is the Raspberry Pi and my solderless breadboard. Okay, but at least I measured everything, so like I can see that in theory it's gonna fit in the board, and at least I can like put this on the lid for now to like move it around, because as you just saw my one-handed grab, I have to move this stuff around because these wires, my cat just thinks they're mouse tails, obviously. So the difference between the lid and the box is obviously the box is where these will sit inside. But if you can kind of see on the bottom of this Raspberry Pi here, this came from, if you're a real hardcore watcher, real hardcore OG, then you've seen my Raspberry Pi cluster video. It still is my most watched video, and it's cringe as hell for me to watch, even though it's like I put a lot of effort into that video. But that was like the depths of COVID, and it was like the eyebrow mustache situation, and I wasn't sleeping a lot, so like I had huge bags under my eyes. It was just like I look rough in that video. But I just pulled this straight off of the stack of 4 Raspberry Pi 4s that made up that cluster. So that's where this little base part came from, that has these like little feet, and then the standoffs for the Raspberry Pi are on top, but then there are these additional standoffs, which are the holes, which are then for like the other layered Raspberry Pis to go on top of. But I'm just like, okay, I'm going to just set this in the box, and then I have little standoff legs that will go through these 4 holes in the box, okay? And then I'm just going to set the solderless breadboard in here. And then I don't have really, and I might as well just like unplug it, but I'm not going to. I have my ADC on here right now, but I'm additionally going to put the stepper motor driver on here. But this is another problem. I'm going to get to it in a sec. And then I have this switch for the 12 volt power supply, which in the box, I might even like show the 3D print models, the CAD models on screen or at some other point in this video or in another one. But I made holes in the box so that I can feed this wire through one of the holes in the side. And then the switch is like hanging out outside. So inconvenient part of it is that, okay, I also put holes in the box for like the Ethernet port, and like the USB ports will be accessible for the Raspberry Pi. And then there's another hole on another wall for the USB-C power supply. You could also access like the was it like 3.5 millimeter audio jack, the micro USB ports, even though I don't use those. But the way it's going to work is I plug in the 12 volt power supply, and then I can flip the switch, boom, turn it on. And that's connected to the stepper motor driver. And then I plug in the USB-C, Raspberry Pi is powered on, okay? And there are all these wires. So then there's another hole for all these wires to come out of for like going to the motor. And then I gave it enough height so that when I put the lid on, it just kind of like gently rests down on these jumper wires that are going to the GPIO or the I2C headers on the Raspberry Pi. Okay. More problems with the 3D printing though. So I needed to make the Scotch yoke, and this is all I made. Okay. I realized like 20 minutes before leaving that there were probably settings in exporting the sliced file for the 3D printer that dictate like how fast does it print the first layer? How high is the nozzle over the print bed when it is printing? What is the print speed that the nozzle is going at? Because I mentioned that I had the Scotch yoke, which is like, this is the crank, and then I had a lever, and then I had a few screws. And like the lever, which is basically this like kind of like a rounded edge ruler with a slot through it and then an output pivot hole, it just like, it started printing the first layer of the Scotch yoke and then printed like the base of the heads of some of the screws that were part of that file. And the first try, like the heads of the screws just like blew off the print bed. And I like tried like 3 or 4 times, like several times to like get the thing going. And then it got to the edge where the lever was starting to print, and it just like, the PLA would not adhere to the print bed, and it would like print a line, and then it would like round the edge of the lever, and then it would like start going back, and then when it just printed, it would like lift off, and then that would get stuck to the nozzle, and then the nozzle would be clogged, and it would just be like then circling around like the pivot hole in the lever, and it's just like spitting out PLA, and it's just clogging it even more. And I was like, oh God, this is like not good. So I like aborted it, and there would be like, they call it spaghettification, I guess is the term, where like, stuff would get kind of clumped up and it would get stuck on other parts. And then the nozzle would move, and then it would like lift off what it had just printed. So I was like, okay, I'm just going to keep this at least for reference to see, the dimensions of what I'm working with right now. And, maybe it's a blessing in disguise, because I have the stand here with the motor, and the center of the crank is supposed to go on the D shaft of the motor, and the hole is too small. Likewise, I had intended for these holes to be 5mm diameter M5 holes. So here's an M5 shaft, and likewise, it's too small. So I need to change that. And there's also the first hole. See that one that's like right above the D shaft in the center? That's like basically touching it, and it's touching like the next one. Okay, that first one that's like 10 degrees is the setting it corresponds to. It is like running up on where the D shaft is. So if I make this bigger, I have to kind of like change where those configuration holes are. And so yeah, it's kind of maybe like a good idea that I had this like little dry run. But like I said, none of the screws printed meaningfully. It started like the outline of the head of the bolts or the screws, whatever you want to call them. Yeah, it was bad. Okay, moving on. Then, while I've got this piece in my hand, this is the output. This is supposed to go up here. I have this ruler up here because I was trying to figure out, okay, I make this modified mount, and you can probably visibly see it's like sagging away from being parallel, right? Okay. This one is basically parallel. I have my level over here somewhere. Maybe I put it away, but this is like 5 degrees below parallel. So I was like, okay, I'm going to design another motor mount that compensates for that. Okay, well, assuming that works, then this is where the output of the Scotch yoke would be, okay, is up here. And so I needed to make something that could attach to this vice clamp. It's kind of like how I explained in the earlier clip. Okay, imagine this is up here. This is spinning. I've got the crank here, and then there would be a lever going in between up to here. So this is going around, and the slot that I've selected for whatever angle, it's like sliding up and down the slot of the lever, okay? And then it's oscillating, and it's right here, okay? So I needed to make something that would mount this, threaded bearing shaft deal, and it's like 8mm on the threaded off the shelf part. So I had to get a coupler, and then it goes to M5 rod. Okay, well, that also didn't print. Kind of like goes without saying at this point, but I did at least correctly get the holes of where I'm going to screw this piece onto, right? Because it fits flush. They're also a little bit small, but then I can put this and it'll fit and it'll be all good, okay? I have enough clearance with the rough dimensions to like slip this guy in here. Okay, so that was another learning experience. Now, we're getting to one of the more tragic parts of this, which is the board enclosure box. So I mentioned 2 other files. There was the crank, yoke, lever arm, and this, mount piece with a few screws. Then there was the modified motor mount with several screws and washers. That was another file. Each one of those, the projected print time was like 2.5, 3 hours, okay? The lid took like 4 hours, and the estimated time was pretty close to the actual elapsed time for the print. So, and I've, done the magnetic encoder attachment on the back of the motor before. So like these are pretty reliable estimates of how long it takes to print. Okay, the board enclosure box estimate was like 6.5, 7 hours. Okay, so I got there at like 11 o'clock. And obviously right now it's like 4:47. Hypothetically, it wouldn't be done printing yet. But like 2 hours in, the corner of the base started warping and lifted off of the print bed. So this one was actually had the best start. Like this one, I was able to I started immediately because I was like, okay, this is the wall time. If I'm doing the parallelization of these processes, what's the total wall time? It's going to be whichever one's the longest. Okay, I'm going to start that one first. Okay. Think like a computer scientist, software developer, whatever. Anyways, I started this one and it was like, okay, the base is just a rectangle. Easy enough. Should be all good, right? Wrong, because it kind of goes with maybe like the thermal problems that cause like the wrinkling on the lid, and it lifted up. And so I had to stop it because I was like, okay, the nozzle, it's like the last part was like over here in the middle. It had already gotten to the edge, started going diagonally this way, and then this corner started lifting off. So I was like, okay, it's going to take like another 30 minutes, but then by the time it gets back, this has already lifted off. It's going to hit the nozzle, and the nozzle is hot. It's going to melt this. It's going to like peel it back. I was like, okay, I'm going to just kind of like these other parts, use it for making sure that my dimensions are good. And just in case the lid, because I didn't know if the lid was going to work or not, the lid did work. But it's like, okay, this is the same size as the lid. So it's like, obviously I saw that stuff in my design beforehand. But yeah, so I looked into it and it was like, I realized there are settings. I probably already said this because I'm just rambling, but there are settings when I export the file that I actually put into the 3D printer. Because like first, okay, I use this CAD OpenSCAD software. It's free. You basically like write lines of code to dictate what your geometry is. It's not like a GUI where you like drag and do stuff. You have to like write lines of code in order to make it. So I was like, okay, I can do that. And I was able to see, okay, that's all good. Then from there, you export it to a 3MF file, which is then in the Prusa Slicer software, which is like same brand as what the brand is for these 3D printers. Okay, it's like a Prusa MK4. And there's like 6 of them at this workspace or whatever. And you import that in. 3MF is kind of like STL from what I understand. And then you slice that and you get the G code. You put the G code on a flash drive. You put the flash drive in the 3D printer. You start it up. And there are settings in Prusa Slicer that dictate like how fast it prints the first layer. I thought, oh, maybe I need to add brimming. Maybe that'll prevent it from like when it, just shoots off, it won't like drag that first layer off. That didn't help, but I need to include it when I do it again. Like for the screws and the washers, that'll probably help. And I need to add in like supports for the off-hanging, 5-degree modified face of the mounting bracket for the stepper motor. So I like tried to change some of that. I tried even like taking away the lever arm to see if like, oh, maybe I could print like the crank and like a bunch of screws and then just like make the lever on its own. Whatever. I'm going to be able to probably just modify the print settings in Prusa Slicer and get it to work. So, but I didn't really get a lot done. You know me. I am young Ebenezer Scrooge. I don't pay for Wi-Fi here. So I was using their Wi-Fi, taking care of business, and didn't get a whole lot done. And I didn't, some other people came in a few hours in, and they were going to use the 3D printers. And I wanted to like ask them for help, but like they had like their headphones in, or they were like doing some like meeting. One guy seemed like he like was the guy who's in charge of like the building, because he was talking about how he like got a ridiculously good deal on the lease and all this stuff. So I couldn't really ask him any questions, but I wanted to be like, yo, if you guys are like using this, do you have any like tips for like what the hell happened with mine this morning? But I think I figured it out. Anyways, so I didn't get a lot done, and I only figured those things out like later. And I was like, okay, I've been here for 4 hours. I'm going to call it a day. I'm going to regroup, circle back probably on like Monday, because if other people are using it and it's going to take like 6 hours, hypothetically, if this were like, Skunkworks wartime schedule, I would have fixed it like while I was there and then like kicked it off. Or, I could fix it now, go back, start it, have it run overnight, watch the first 15, 30 minutes, leave, because the box is going to take 6, 7 hours, probably a little bit longer if I add brimming around the base. And then, I'll go back tomorrow morning and there won't be like contention because like who else would go and like 3D print stuff overnight? Probably a lot of people, but okay, more reflections. Earlier this year, I renewed my membership at that place, which is monthly. It's like $30 a month. Jiu-jitsu is like $200 a month. I'm on another hiatus from jiu-jitsu because, we won't go into that now. But that's like, 6-7 months of the makerspace at the rate of 1 month of jiu-jitsu, right? So, okay, $30 earlier this year, and I didn't go and print it all. So that's kind of just like, okay, sunk cost. So today I renewed my membership again, $30. And then the 3D printing is like ridiculously cheap. Like I spent $8.50 total for reserving the entire time. Cause that's how it works is you like reserve for the amount of time and then that is how much you pay. And kind of loss on my part. It was kind of a loss because I only printed the lid, which was 4 hours, and that's like $2.50. The box was like $4, and then like the other two separate files of like miscellaneous parts were like $1.50. So, the numbers I just said probably don't add up to $8.50, but that's how much it totaled out to be. It's like ridiculously cheap. So it's like basically you're paying the cost for the parts in the monthly membership. So it's like I should get this done in a month, especially because I've had this like first trial round and like the magnetic encoder, that part and everything, I just like got online and I just like boom, drag and drop, plug and play, and it was like good to go. This I completely made from scratch. I downloaded like for the nuts and the screws, STL files that I imported into OpenSCAD, and then I like, laid it out, and then, but like I completely designed the Scotch yoke on my own. Like I figured out where all these holes should be and everything like that in order to get the angle on the output. And I was like figuring out, how am I going to get it all on this clamp stand with how much height that I have to work with and stuff. So, I didn't realize the whole getting the first layer speed worked out and all that were things I needed to keep in mind. But, I have 30 days left on my membership. I have until May 10th. So, okay, other problems that I have to work on in the meantime. I was like showing you guys, this is the stepper driver motor. This is going to go on the solderless breadboard. Problem is, I made the same mistake that I made with one of the earlier ADCs is I did not install the pins correctly. I flipped them upside down because I was thinking, I'm going to put them vertically and then put them right on the board. Well, in hindsight, I should have the pins going beneath the board so that I can put it in the solderless breadboard and then put the connections in the same row on the breadboard and then loop them back to the Raspberry Pi, because then this will be snug on the board, whereas it's like freestyling, free balling now. So I've got another one, got to resolder that. And then I have, these are the op amps. I'll get to that in a sec. These are the new Hall sensors. These are the greatest magnetic sensitivity Hall sensors with my voltage range that I'm working with that I could find. Okay, I've got 5 volts that I'm working with from the Raspberry Pi, and that's the maximum, or it's like the rated VCC. I guess it is the maximum because you could use 3.3 volts or you could use up to 5. But between negative 5 volts and 5 volts on these Hall sensors, you have magnetic sensitivity of 176 millitesla. Problem is, like I said, the magnet that I'm swinging through is an N52 neodymium magnet. So at the face of the Hall sensor, that could be like 65,000 Tesla. Okay. So I'm like, well, I'm going to make a new base for this stand. One of the problems is that the base of the stand right here is metal. So as the magnet's swinging through, there's probably going to be eddy currents. And, we're trying to minimize stupid causes of interference. So I'm going to make a new base where this is going to be basically, instead of like right above the base how it is now, there's going to be kind of like a well, and it's going to be made out of wood. And then I'm going to put the Hall sensor in the base of this well, or this cavity, I'm going to call it. And that way, the magnetic field strength from how far away the magnet is will be within that range. So it's like if VCC on the Hall sensor is 5 volts, then 0 volts on the Hall sensor is negative 176 millitesla. And so VCC over 2, so 2.5 volts, is where the output is corresponding to 0 Tesla, okay? 0 magnetic field strength. So from 2.5 volts to 5 volts, that's where the positive magnetic field sensitivity range is. So I need to amplify the top end and the very bottom end, basically, of the readout from the Hall sensor, because the field strength is going to be so strong, essentially, that it's going to be approaching the saturation level of the Hall sensor. The Hall sensor magnetic sensitivity is really linear, thankfully. I was using another kind of like the Hall sensor that you just like get when you first Google Hall sensors. It doesn't have like a very good linear range. Okay, this one does have a good linear range. So how do I amplify the linear range that I'm looking at? That's where these op amps come in. So I'm going to put the stepper motor driver, boom, on the solderless breadboard. Boom, one of the op amps on here, because the op amp that I got, the form factor, it contains effectively 2 op amps. Okay, so you can have like the idealized 1 op amp. This integrated circuit contains effectively 2 op amps. So I can amplify both of the ranges that I'm looking for. Put those on the breadboard, and then I'll have it all in the box. That's the thing. And then it'll all be like, okay, Raspberry Pi, boom, everything's on the breadboard, and then boom, wires all coming out of just like one hole. And then I can have, the motor, the coil, everything going in that one hole. And then I have one other hole for the 12-volt power supply switch. So it's going to clean up the setup considerably. And so that's like the idea behind that. But then it's like, okay, I have to reprint all this stuff, and then I have to put the Hall sensor and stuff together and the op amp and make, voltage dividers and stuff. I have, some resistors that I got laying around so I can work with that. And I have to determine the dimensions of that like new wooden base that I'm going to make, so that I know how far away, how high to make it, so I can put the Hall sensor an appropriate distance away, so that when the plastic protractor is at the maximum amplitude or the max magnitude of the angle, because it's like maybe positive negative 60 degrees, positive negative 45 degrees, positive negative 30 degrees maybe. I need to figure out what the magnetic field strength is depending on like how far away that Hall sensor is from like how strong is the field strength that it's picking up when it's swinging through that. So I'm probably going to like tape it to a poster board and then just like slowly move the Hall sensor up and down and have like the magnet taped at, different angles, like max, min, throughout like, 10, 20, 30, 40, 50, 60, and then, raise and lower the Hall sensor and then get the readout. And then I'll have all of it, the dimensions of the base figured out. I'll have the mount. I can have the Scotch yoke all set up. That way I can determine the angular velocity that I can swing this thing through. It's come together. It sounds like, in my head when I'm thinking about it, I'm like, dude, yeah, I'm so close. But then, it's probably going to take a little bit of time. But this has actually been a very engaging project. So, this is going to be a pain to edit because it's a pain to edit when I ramble. But having a YouTube channel, you just do so much editing. Anyways, see you guys in the next one.